Hello, I am Olivier Hénard, and today I will talk about joint work with Nicolas Curien entitled Parking on Critical Galton-Watson Trees. So if parking on the line is known for quite a long time ago now, parking on more general directed graphs has been introduced quite recently only in Brunner and Panholzer. So in our case, we'll be interested in parking on trees. So let T be a rooted tree. We have an example here on the left. Each vertex of the tree is a parking space that may accommodate at most one car. When a car arrives on its favorite vertex, it will try to park there if unoccupied, or proceed on its way down to the route and park as soon as possible. So for definiteness, we assume that the cars are given an order. So there is first car, second car, third car, fourth car, and so on. The first car arrives here and can park without problem here. The second car arrives at the same spot, so there is a collision, which is resolved by putting the second car on the farther of that vertex. For the third car, there is no problem, as you see. The fourth car, there are two collisions. It tries to park there and there, but it's already occupied, so it parks at the grandfather. For the fifth car, it will go down to the route where it manages to park. For the sixth car, there's no problem. For the seventh car, it cannot park on the tree because the cars go down only, and so it contributes to the so-called flux at the root x root t, which is equal to 1. The other fluxes along the edges, that is the number of cars that traversed that edge, are denoted here in red. Final configuration here. You can find occupied parking spaces in blue and free parking spaces is the complement of the occupied parking spaces. A crucial observation is that the configuration after parking does not depend on the order of the car. This is an abelian property, which is also visible from this alternative definition in terms of LU, the number of cars with favorite parking spot, vertex U. So in the initial configuration, number of cars that arrive at vertex U. XU, the flux at U, is defined as the number of cars going down from vertex U. XU satisfies this equation. XU is the sum over the children B of U of XB plus LU minus 1, and I then take the positive part. A related quantity is YU, the number of cars that wish to park at U in the parking process, that ever wish to park at U in the full parking process. YU is simply related to XU by XU equal YU minus 1 positive part. And YU satisfies recursive equation on its own. YU is the sum of the children B of U of YV minus 1 positive part plus LU. Of course, this recursive equation have to be solved downwards from the leaves. And if U is a leaf, then the sum of the children is an empty sum that has to be understood as 0. So the probabilistic model we'll be interested in is to take force T, capital Tn, critical Galton-Watson tree, conditioned to have n vertices if possible, with offspring distribution capital N. And the other parameter of the model will be the car arrival distribution, LU. The LU will be IID according to L conditionally on Tn. Now, the question we'd like to address is the behavior of Xn, which is Xn of the roots for the tree Tn. So the flux at the root in a large conditioned Galton-Watson tree. And we expect to see a phase transition to be phrased in terms of L and N. L, the car arrival distribution, and the offspring distribution. Key tool for this, and this was already a key insight from Goldschmidt-Plekuski, is to consider the quantity X and Y for the same tree but unconditioned. So for T, the non-conditioned Galton-Watson tree. Why? Because it does satisfy a simple equation, recursive equation in distribution. So for Y, for instance, we take this form. Y is the sum of the I from 1 to n of yi minus 1 positive part plus n. And when confronted with such an equation, it's natural to take the first two moments. This is precisely what Goldschmidt and Plekuski have done. Taking the first moment and using Valls lemma, they conclude that the probability that y is positive, meaning that a car is parked at the root of t, is equal to the expectation of the car variable distribution. Also, if the second moment of y is finite, then computing variance of y, they find that variance of y is equal to variance of y plus a certain quadratic polynomial in expectation of y, whose coefficient a, b, and c are function of expectation of L, variance of L, and variance of n only. This leads to an explicit formula for the expectation of y in terms of these three parameters only, and a conjecture from Goldschmidt-Plekuski concerns the location of the phase transition plus the expectation of y given by this formula. In our work with Nicolas Curien, we are able to confirm this conjecture. We set m, sigma 2, and zeta 2 for the expectation of L, the variance of L, and the variance of n, calling that the expectation of n is 1 by criticality. And we are able to delineate a subcritical phase from a critical phase from a supercritical phase in terms of this real valued parameter theta. Theta is positive, we are in the subcritical phase. Theta equals 0, we call it the critical phase, and theta negative, the supercritical phase. Why do we coin this subcritical, critical, and supercritical? Well, this will be seen by the property in the tables. So, first line of the table, we give zeta 2 expectation of x plus expectation of L minus 1. So expectation of x is the unknown quantity, the other are parameters of model. It is equal to minus square root of theta in the subcritical phase, 0 in the critical phase, and plus infinity in the supercritical phase. This, of course, gives back expectation of x, but also expectation of y, and hence solves the conjecture by Goldschmidt and Plekuski. For xn, the flux at the root of Tn, a large critical Galton-Watson tree, which was a quantity of interest, it will converge toward the finite limit law in the subcritical setting. It will diverge, but sublinearly in the critical phase, and in the subcritical phase, it will converge towards the constant c, when we normalize by n. So it is a linear divergence towards a deterministic constant, and this deterministic constant L also appears in the third line of the table, where we compute the probability that a car is parked at the root of t. This is m, the expectation of L in both the subcritical and critical phase, and m minus c for the same constant c in the supercritical setting. Key observation is that the first two moments of L and n are indeed sufficient to describe that phase transition. Now, further remarks concern the strange-looking quantity zeta 2 expectation of x plus expectation of L minus 1 that we put in the table. Why to consider such a quantity? Why is it natural to consider? Well, it's natural when considering parking on the Keston tree T infinity. This Keston tree is the local width limit of the trees Tn when n goes to infinity. This is an infinite tree with one edge, and it consists in an infinite line of distinguished individuals called the spine, here in red, that reproduce independently according to the size-based distribution n hat of n, whereas the other individuals that are not distinguished reproduce according to the normal distribution, giving Galton-Watson trees. When considering parking on a tree and projecting onto the line formed by the spine, we find that the car variable distribution at a distinguished vertex has a mean, which is precisely given by the zeta 2 expectation of x plus expectation of L, and it is then important to compare this quantity with 1, which is a crucial parameter for parking on the line, in a single line. Two other remarks are that the scaling of xn in the critical case depends on finer details of L and n than the first two moments. This is ongoing work, and the same is expected to be true for the value of c. Now to quick element of proofs. First, for solving the conjecture, we use an interpolation scheme with a time parameter t varying between 0 and 1. At time 0, the car variable distribution L0 is direct measure as 0, and at time 1, it is the original car variable distribution L. At time t, we call xt the flux, the number of cars that not manage to park on the tree at the root. And x0 is 0, whereas x1 is x, our quantity of interest. We are able to compute the differential of expectation of xt with respect to t and find, using the many-to-one formula, a simple expression in terms of expectation of xt only, an ODE that we're able to solve to give back the conjecture. When using the many-to-one formula, the spine, we end up doing parking on the Keston tree and the apparition of this strange Rookie quantity that we just explained a moment ago. As for the second point, it concerns the fridge subtree theorem of Aldous and Jansson. Let Tn be a Galton-Watson tree and n vertices. We call up Tnv the subtree of Tn above V and consider the empirical measure of these fringe subtrees, so summing over V, and we have convergence in probability towards a deterministic probability measure that is the Galton-Watson measure, the original Galton-Watson measure, integrating against this function ftv, which is the indicator that a car is parked at the root of t. We end up with this limit statement, and then by conservation of the number of cars and using the standard law of large number for this ratio here, we are able to get the law of large number alluded to in the table. So here are some further references, some of which I already mentioned, and I also encourage you to have a look at the extensively growing literature on the related Derrida-Otto model, which is a parking model of the complete environment tree, which is maybe seen as a supercritical Galton-Watson tree. And for this kind of trees, the asymptotic are supposed to be quite distinct from the one that are known in this critical setting or conjecture. Okay, that's it for me. Thanks you all for watching, and see you at the question session. Bye-bye.